Definite integrals, part 1. The net area of R is the area of the parts of R that lie above the x-axis minus the area of the parts of R that lie below the x-axis. In the last section, we introduced the Riemann sum, which is used to estimate net area. As the number of subintervals increase, the Riemann sum approaches the net area. Find the midpoint Riemann sum of f on the interval from 1 to 3 using 4 rectangles. Notice that each subinterval is of length 1/2. Let's look at the midpoint formula. The midpoint Riemann sum uses the midpoint of each subinterval to evaluate the given function, and we're going to use the formula for the midpoint Riemann sum. We use the formula to find the midpoints. A is equal to 1. Change of x is equal to 1/2. Next, we simplify the expression. Since there are 4 rectangles, k runs from 1 to 4. Use this information to set up the summation. After you set up the summation, use one of the methods discussed in the previous section to evaluate the summation. Notice that we get a negative answer. The Riemann sum is the negative of the area bounded by the curve, because from 1 to 3 the curve is under the x-axis. Let's do another example. Find the left Riemann sum of f over the interval 0 to 3 using 6 rectangles. Each subinterval is of length 1/2. The left Riemann sum uses the left endpoint of each subinterval to evaluate the given function. For this Riemann sum, a is equal to 0, change of x is 1/2, and k runs from 1 to 6. Simplify the expression, and then set up the left Riemann sum. After you set up the left Riemann sum, evaluate using methods of the previous section. Again, we have a negative Riemann sum. The area of the rectangles above the x-axis is less than the area of the rectangles below the x-axis, so the overall result is negative. The general Riemann sum allows for intervals of varying lengths, and the chosen point x bar doesn't necessarily have to be a left or right or mid. It can vary as well. We have been doing midpoint, left, and right Riemann sums where the length of each interval is uniform. There are other ways of doing a Riemann sum, but we're not going to be investigating those other ways. Just be aware that there are other Riemann sums. The definite integral, what does that mean? The definite integral is the result of an infinite Riemann sum. We say that a function is integrable if the limit exists. Now this limit thing requires some explanation, so let me talk about that for a minute. When we have subintervals of uniform length, saying that the number of intervals increases without bound is enough. This definition is written for the general Riemann sum, where the lengths of the subintervals may vary. The expression delta going to 0 ensures that all the subintervals are converging to 0 while the number of subintervals increases indefinitely. To say that the limit exists and is unique means that not only can the limit be found, the limit will be the same regardless of which type of Riemann sum we choose. So by this definition, if we know that a function is integrable, then all infinite Riemann sums have the same value. Now, what kind of functions could possibly have this property? We'll find out in part 2. Take care and have a great day.